Swayam Prabha. Digital India. Educated India.
So, in your undergraduate program, BTech, wherever you did a lot of courses in mathematics, right? You must have done a course on linear algebra where you were solving some equations. You must have done a course on ordinary differential equations. You must have done a course on partial differential equations. So, you have done a whole bunch of courses, and during those courses, most of the time, I mean, you were looking at the particular course, the kind of methods that were taught in that course, and they were all standalone. I mean, you say, okay, if this is the equation, I am going to solve it this method. If this equation comes, I am solving it this method. Okay, and it looks like most of these methods are very specific to the particular problems that you are solving. Okay, and as you go for masters and as you go for PhD, what you want to do is you want to develop a overall perspective about a subject. Okay, and what I mean by that is you need to see if the different methods that you have learned or different problems that you have encountered, linear algebraic equations, ordinary differential equations, partial differential equations, can they all be solved in a same framework? Okay, because then you realize that you need to understand this framework and then you can use it to solve any problem. It is not that you need to remember certain methods, techniques for one kind of equation, another technique for another kind of equation, another technique for a third kind of equation. Okay. So, is there a basic framework, is there a basic thing which connects these different classes of equations? And if you understand this basic framework, that is what we are going to develop in this course, that different mathematical techniques that you have learned in the past, they are actually not disconnected. We can think of putting them all in a particular framework, and then you are trying to analyze all these different classes of equations in the same framework. Okay, that is the whole objective of this course, if I want to put it in a nutshell. So, if there is a particular concept in algebraic equation, how can I extend it to ODE, how can I extend it to PDE, and vice versa. So, every concept in one particular system has an analogous concept in another system, and if you can think along those lines, then there is some maturity which you develop in your thinking, which is going to help you in the long run, because what we do is try to connect dissimilar things. Okay. So, things may look dissimilar, but they are actually not dissimilar, that is what I am trying to say. Okay. So, the objective here is to develop a framework So, we are going to talk about linear algebraic equations, linear ordinary differential equations, and linear partial differential equations. So, we are proposing to develop a framework which can solve these different classes of equations, okay, algebraic, ordinary differential equations and partial differential equations. So, I think the most important word in all of this is the word linear, because as long as those equations are linear, we can solve them analytically with a paper and pen. You do not have to necessarily go to a computer, you do not need a calculator. In fact, I want to emphasize no calculators in this course, okay, no computer programming, I mean almost, okay. So, because, so we restrict ourselves to linear equations as we can them so we can do an analytical solution, okay. So all you need is a paper and pen and understand the technique, and of course some calculations have to be done, but we will as far as this course is concerned stick to analytical methods, and if necessary you have to do something numerical when you are doing research, then you may have to write a code, okay. But as far as this code this course is concerned, I do not think there is going to be any MATLAB programming or any programming, okay. So, what are we trying to do as chemical engineers? We try to analyze the behavior of systems, okay. It could be reactors, it could be distillation columns, it could be heat exchangers, anything. And what we want to do is we want to understand how a particular piece of equipment is going to behave. You could do this using two methods. One is by doing an experiment, by actually running the plant, okay, or running your lab equipment and understanding what is the temperature profile, what is the velocity profile, making measurements. This is one approach. The other method is by doing what is called modeling and simulation, okay. So basically whenever you have any system, you have two approaches for working on, okay. So there are basically for analyzing a system. One is the experimental approach, where you actually run the system and take measurements and try to understand the behavior, okay. Here we run an experiment on the system, make measurements. For example, if it's temperature, you will put some thermocouple and make measurements, okay, and determine the system behavior. Now, what is the advantage of this method? The advantage of this method is that assuming you are running your experiment perfectly, you are not making any mistakes, that whatever information you are going to get is actually truly representative of the system behavior, okay, because that is how it is behaving. What is the disadvantage of this method? The disadvantage is that whatever you are doing is very specific to that particular system. If you want to change something, the flow rate or the material of construction or anything, the behavior will change. Again you have to redo the whole experiment, okay. So you are not able to generalize whatever you have done if you follow a truly experimental approach, okay. So this is definitely very accurate, but specific to the system studied. It cannot be generalized. That is the problem. What do I mean by generalized? If you want to do for a different system, then again you have to run the experiment again. Okay, so it becomes more intensive, labor intensive. You have to again run the experiment, do the measurement. The other alternative that you have is, we have what is called this is the second alternative, the theoretical approach, which is basically also called modeling and simulation. That is the alternative approach that you can take to analyze the system. So, what do you do in modeling? When I say modeling, what I mean is I recognize the fact that every system has to follow the law of conservation of mass, momentum and energy. Okay? Those laws cannot be violated. So, for every system you will write down, modeling is basically writing down the laws of conservation which are applicable to that system. Okay? So, basically we write down the law of conservation of whatever it is, depending on the particular system, maybe need all three, momentum and energy. Okay? So, basically when you do this, what do you get? When you write down these laws, you will get a bunch of equations. Okay? So, you have these equations basically represent the behavior of the system, and when you have to solve them, that is what I call simulation. Simulation is basically solving these equations. Okay? Is solving equations which arise from the modeling. Okay. So, basically the law of the modeling gives rise to equations. These equations are great, but you have to solve them, only then you can predict what is happening. So, for every system you can do this. Now, what is the advantage of this? Because these are basically based on some fundamental principles, you can apply to any system. Okay. So, if you are talking about distillation column, it could be benzene toluene separation, it could be some other separation, it does not matter. But what is the problem here? The problem is that when you are doing modeling, you will make some assumptions. Okay. You have assumptions which you make, and those assumptions may or may not be valid, and that is the limitation of the modeling approach. The modeling approach is a general approach. So, the problem of being specific here has been overcome, because I can just change the physical properties of the system, the whatever other properties I can change, and I can do the simulation. So, it is general, but in the process of doing the modeling, you may make some assumptions. You may say, okay, flow is laminar, or you may say, I am assuming ideal gas law, which may or may not be valid. So, those assumptions may break down. Okay. So, only, and how can you find out whether the assumptions you are making are valid or not? Only by comparing the predictions of the model with experiments. So, the point is you need both. modeling alone is not enough, experiments alone is not enough. You need to have both to get a good understanding of the system. Okay. So, this is based on assumptions which may not be valid. Okay. So, the assumptions are not valid, then your model is incorrect. Okay. How do you know if these assumptions are valid or not? You have to compare with experiments. Okay. So, we need to validate by comparing with experiments. The advantage here is that it is general. Okay. I can use, once I develop the model, I can use it for any system. I can change the length, I can change the diameter of my pipe. I just have to go to my equation and change the diameter of the pipe. I can just go to my equation, change the length, change the flow rate. Okay. That is what I mean by general. So, this is general as opposed to being specific for the experiment. Okay. And that is the advantage of this. So, general as it can be used for by changing parameters. Okay. So, as far as this particular course is concerned, we are definitely not going to talk about the experimental methods at all. We are going to talk only about the theoretical approach, where we are looking at the modeling and the simulation aspects. Okay. In fact, we are not going to talk too much about the modeling aspects, because that is what is being given in most of the courses. You are doing a chemical reactor theory course, they will talk about writing down the fundamental laws for that particular reaction or that particular reactor. Okay. We are going to focus mainly on the simulation aspects, and again we will talk only about linear systems. So, that is the idea. So, but anyway, to begin with, I mean rather than jump directly into equations and starting to solve, to set the background, and we will take one or two examples to begin with and show how the model is developed, and how you can possibly cast it in the form of equations which we will be using later. Okay. So, I will begin with an example, and that will make it clear. So, just an example of model development and writing in a standard form. That is what we are going to talk about, okay, right now. So, the example I am going to look at is flow through a network of pipes, and to keep things simple and to just illustrate the concept, I am going to look at a simple bifurcation in a pipe. Okay. So, I have this pipe network, this diameter of this pipe is D, this is D1 and this is D2. Okay. So, basically what we are trying to do is we are trying to analyze the flow behavior through this channel which has a bifurcation. So, one channel is breaking up into two channels. First channel has a diameter of D, second channel has diameters D1 and the third whatever, okay, D1 and D2. And the length of this is L, length of this is L1, length of this is L2. So, by way of motivation you can think of real pipelines, you know, you will have one pipe and then some other pipe being taken off, okay. Or if you are more interested in something not chemical engineering, you can look at the flow of the blood through the circulatory system, arteries branching into arterioles and things like that, okay. But that is a much more complicated system because there are too many of these bifurcations there. But to illustrate the idea, we just look at one bifurcation. What I want to do is, I want to talk about the problem where I am going to specify the pressures at the inlet and outlets, okay. And you have to be very clear whenever you are trying to solve a problem, you have to understand what the problem is, okay. So, the problem here is I am specifying the pressures and I want to calculate what the velocities are, what the flow rates are through each of these channels, okay, through each of these limbs. So, I am going to say P in is specified here, P atmosphere is specified here, P atmosphere is specified here, okay. So, let us say these two limbs are exposed to atmosphere, that is the pressure, and I have given the length and this thing, and question is we specify the pressures and want to find velocities in each channel, okay. So, I am going to call this velocity V, this velocity V1, this velocity V2, okay. And clearly this liquid which is flowing, this fluid which is flowing has some viscosity mu, and because there is only one liquid, the viscosity is mu in all the channels, okay. The viscosity is mu. So, what I want to do now is try and get these velocities, and so first I am going to talk about conservation of the momentum. Now, this is just to illustrate, okay, the modeling aspect. This is the modeling part I was talking about. So, when I am talking about conservation of momentum, you are looking at finding relating the pressure drop to the velocity field, okay, and you are familiar with the Hagen-Poiseuille equation, which is valid as far as laminar flows are concerned. Your flows laminar, you can use the Hagen-Poiseuille velocity. So, now I am going to say this pressure here is, let us say, junction, pressure of the junction. I am going to write the expression for P in minus P atmosphere through this channel, through the upper limb, okay. So, P in minus P atmosphere is P in minus P junction plus P junction minus P atmosphere, okay. I have just added and subtracted P junction, that is what I get. And assuming the flow is laminar, and this is what I said, when you do modeling you make assumptions. So, I am assuming the flow is laminar, okay. This pressure drop is going to be given by something like 32 mu L by d squared V. This is the pressure drop in this pipe, okay, and in this pipe here it is 32 mu L1 by d1 squared V1, okay. Similarly, I can do a momentum balance by including the lower pipe, okay, and I would get P in minus P atmosphere equals 32 mu L by d squared V plus 32 mu L2 by d2 squared V2, okay. So, basically this is the part which is the modeling part, where I have just applied the conservation of momentum equation. Okay. So, I told you modeling gives you equations, these are the two equations which we have got. But now, how many unknowns do I have? I have 3 unknowns, V, V1, V2, okay, but I only have 2 equations. So, I need one more equation, otherwise I can't really solve, otherwise I have to specify the velocity, okay. So, what I have to do is see if I can get one more equation, and that is going to come from the conservation of mass, which tells me the flow coming in here at steady state must be equal to the flow to the other 2 pipes, okay. So, I am going to say V multiplied by d squared must be equal to V1 d1 squared plus V2 d2 squared. Okay, all of this is multiplied by pi by 4, which is the area. So, because pi by 4 is common, I can cancel it out, okay. So, I can just get this, okay. So, basically this is your conservation of mass, this is my conservation of mass. So, now I have done the modeling part for the system, I have gotten the momentum equation and the mass equation conservations, and what I want to do is I want to be able to write this in terms of, I want to solve for V, V1, V2, I have 3 equations and 3 unknowns, okay. And so, what I want to do is I want to cast it in the kind of form which we will be talking about for the rest of the course. And that is, I want to write this system of equations in the form Ax equals b, and that is what you must have seen in linear algebra. When you were doing a course in linear algebra, you would have written in the form of Ax equals b, okay. So, a matrix, X is a vector, this is a matrix, this is a vector, and this is also a vector, okay. So, how can I write those equations in this form, okay, because after this I am going to only be talking about this, I am not going to be talking about modeling at all, I am directly going to jump to equations and talk about methods of solving, but you need to understand that every equation that you are going to solve as a chemical engineer actually has a physical meaning, has a context, okay, and that is the context I was trying to bring here, okay. So, I am going to write this as 32 mu L by d squared V, right. I am just doing some interchanging, you may or may not want to do this, but it is okay. Equals, so I am just writing it and I am going to bring everything to one side and write a 0 on the right hand side. Right. So, I am just moved the minus V to the right hand side, okay, or whatever, I did some rearrangement. So, basically what I want to talk about is X is the unknowns which I am interested in. What have I done? I have written all the unknowns on the left hand side. B is what I will call a non-homogeneity later, is what is fixed. What is fixed is the pressure drop. That is my, so this is like going to be like my B, and I am going to write this system of equations or these terms on the left in the form of Ax. What is x going to contain? X is my unknown. Unknown in this case is my velocity v, v1, v2. Okay. So, I am going to write x as v, v1, v2. I think in the book I must have put it the other way. So, then I write this equation as v, v1, v2, and this is P in minus PA, P in minus PA 0, and this first equation I write it as 32 mu L by d squared, that multiplies V, then I have 32 mu L1 by d1 squared, and I have nothing multiplying V2 in the first equation, so that third term is 0. Okay. And now I have in the other one 32 mu L by d squared 0, 32 mu L2 by d2 squared, because in this equation there is nothing multiplying V1. Okay. So, basically this is matrix multiplication which you are supposed to know. Okay. I am not going to teach you that. So, this row multiplied by this column will give you the first these two terms. This row multiplied by this column will give you these terms, and the last one is minus d1 squared, minus d squared, minus d squared, d1 squared, d2 squared. Okay. So, basically if you do a matrix multiplication on the left hand side terms, you will get these three expressions here. So, what I have done is done the modeling, wrote the equations, and now I am writing this in the form of this is my A, this is my X, and this is my B. So, this is just to give you an idea that there are many systems in chemical engineering where you will have equations of this type showing up. So, what we will do is we will talk about how to solve equations of the form Ax equals B. Okay. A couple of things. Why do I call this a linear equation? I call this a linear equation because what are my dependent variables, the ones which I am interested in finding out? They are occurring to the power 1. Okay. So, look at all the velocities v, v1, v2, they are always to the power 1, they are not squared or any power. So, as long as they are occurring to the power 1, the dependent variable, or if there is a system where there is a derivative of a dependent variable, if they are occurring to the power 1, then it is a linear equation. So, because these equations are linear, I am able to do this. Okay. If this is not a linear equation, I will not be able to write it in the form of a matrix multiplication. So, that is something you have to remember. Okay. I am able to write this in the form of Ax equals B only because these equations are linear, which means the velocities are to the power 1. Okay. And that is the reason we call it linear algebraic equations, because they are algebraic, there is no derivative term. So, these are linear means the dependent variables, in our case it was V, V1, V2 occur to the power 1. Okay. Now, again what we should also realize is, understand similarities with what you have possibly learnt in a different context, especially when you are doing research. You are looking at some problem, trying to solve it. You look at somebody else who has solved maybe a different problem in a different area, and that may give you an idea about how to solve your problem. Okay. So, I want to talk about an analogy of this with something which you are possibly very familiar with in the context of electrical resistance network, resistor networks. Okay. So, for example, this system is analogous to the electrical resistor network. So, for example, okay, this is R, this is R1 and this is R2, and you must have done this sometime before. Okay. And what we do here is we are assuming the voltages are fixed. Let us say V1, V1 and then this is VA and this is VA, just to keep things similar to what we did earlier. The analog of pressure is voltage. Voltage is driving the current, pressure is driving the flow. So, I am specifying the voltage here, I am getting the current. Objective is to get the current distribution. Okay. So, the current is I here, current is I1 here and current is I2 here. So, if you were to do this, and again we are assuming Ohm's law, okay, I am assuming Ohm's law is valid, we would write V1 minus VA is I multiplied by R plus I1 R1, Ohm's law. Okay. Again V1 minus VA is I multiplied by R plus I2 R2. Okay. And if you talk about current, I is I1 plus I2. These are basically what you have come across earlier as Kirchhoff's laws, first law, second law, that is first law then second law. Okay. And again you have three equations. Only thing is the current here is not velocity, current here is the flow rate. The equivalent of current is flow rate, not if you had current density then you have to multiply by area. In the velocity problem I multiplied by area because I was doing mass balance involves balance of flow rates, not balance of velocities. Okay. So, this is like flow rate, velocity was like flow rate per unit area. Okay. So, anyway, so these are things you have to think about, and the point is again we made an assumption here that Ohm's law is valid, and only because of Ohm's law we are saying this is, we are getting a linear equation. If Ohm's law is not valid, then you will get nonlinear equation. So, these equations are similar to the pipe branching problem. Ohm's law ensures linear equations, and again two completely different systems they have similarity, that is something you have to keep in mind. Okay. So, these two systems are analogous. Okay. Let us stop for today.